Before we talk about black holes, it helps to slow down. Black holes are often described as violent, dangerous, or terrifying, but those descriptions come from speed, from headlines, from imagination. The reality is quieter, much quieter. A black hole is not a hole. Despite the name, a black hole is not a hole. Nothing is torn open. Nothing is missing. A black hole is a region of space where gravity becomes extremely strong, so strong that escape becomes impossible. Once a certain boundary is crossed, gravity is familiar to us. It keeps our feet on the ground. It holds the moon near Earth. It guides planets around stars. A black hole is what happens when gravity is allowed to become extremely concentrated, not suddenly, not violently, but through a slow process. Black holes do not require exotic materials. They are made from ordinary matter, the same matter that forms stars, planets, and people. What makes a black hole different is not what it is made of, but how tightly that matter is packed. Black holes are not black because they are evil, or empty, or consuming. They are black because light cannot escape. Light follows gravity, and in a black hole, gravity bends space so strongly that light curves inward. Despite their reputation, black holes are quiet. They do not roar. They do not pull things in violently from far away. They behave like any other object, with the same mass. A black hole the mass of the sun would affect Earth the same way the sun does, from a distance. Most black holes are invisible. They emit no light. They do not announce their presence. We detect them indirectly by how they influence nearby matter and nearby stars. Their silence is part of the mystery. Black holes were not discovered by accident. They were predicted, on paper, through mathematics, long before any evidence was found. Equations suggested that gravity could collapse matter beyond a certain point. Reality later confirmed this. Black holes are not where physics breaks. They are where physics becomes intense. Our current theories still work very well, up to a certain boundary. Beyond that boundary, new understanding may be needed, but nothing magical is assumed. One of the most important ideas about black holes is the event horizon. This is not a solid surface. It is not a wall. It is simply a boundary, beyond which escape is impossible. Crossing it feels normal. Locally, nothing dramatic happens at the boundary itself. Black holes are mysterious, not because they are chaotic, but because they challenge intuition. They force us to rethink a space, a time, a gravity, a information. These are deep concepts. Naturally, they take time to understand. Black holes are not wandering predators. They do not hunt stars. They do not threaten Earth. The nearest known black hole is extremely far away. Cosmic distances are vast. Black holes help scientists test ideas. They allow us to explore how space and time behave under extreme conditions. In this sense, They are teachers, quiet ones. Everything about black holes follows natural laws. There is no intention, no hunger, no desire, only physics, unfolding calmly, inevitably. Imagine a black hole as a region of stillness, where gravity is simply very strong, nothing more. Gravity is always present. It holds your body gently to the earth. It guides the moon in its path. It keeps planets moving calmly around stars. Most of the time, gravity feels weak, subtle, almost unnoticeable. In modern understanding, gravity is not a pulling force. It is the way mass shapes space. Objects follow the curves created by mass. They move along paths that feel natural, effortless, inevitable. When mass is small, space curves gently. When mass is large, space curves more deeply. A black hole begins when mass becomes concentrated into a very small region. Space bends intensely. Gravity does not turn off. It does not rest. It does not weaken with time. If nothing resists it, gravity continues to act. Slowly, patiently, without urgency. In stars, gravity is balanced by pressure. Heat from nuclear reactions pushes outward. Gravity pulls inward. When these two are balanced, a star remains stable, quiet, long-lived. Eventually, fuel runs low, pressure weakens, gravity begins to win. The star starts to contract. This contraction is not sudden. It unfolds over time. Collapse sounds violent, but in reality, collapse is orderly. Matter moves inward, following curved paths in space. Nothing rushes. Everything follows gravity's calm direction. As matter contracts, density increases. Atoms are pressed closer together. Space curves more sharply. Gravity strengthens naturally. Nothing chooses to collapse. There is no moment of intention. There is only physics. Simple laws, applied consistently. Over time, different kinds of pressure can resist gravity. Thermal pressure, quantum pressure, each has limits. When gravity exceeds all forms of resistance, collapse continues. As collapse progresses, gravity grows stronger, not because gravity changes, but because mass becomes more concentrated. The curvature of space deepens. Paths inward become unavoidable. Collapse takes time. From the outside, it can appear slow, very slow. Time behaves differently near strong gravity. We will explore this later. At this stage, nothing about collapse requires extreme ideas. No tearing, no destruction, just matter responding to gravity. As collapse continues, a critical boundary forms, a region beyond which escape becomes impossible. This boundary is calm, invisible, mathematical. Once collapse passes a certain point, it cannot reverse. Not because something is broken, but because space itself has curved too deeply. Understanding collapse is essential to understanding black holes. Black holes are not sudden objects. They are the natural result of gravity working patiently. Collapse does not mean destruction. It means transformation, a change of structure, a new state. Imagine gravity as a gentle guide, not a violent force, always present, always calm. Black holes do not appear out of nowhere. They are not sudden tears in space. They are the final stage of a very long process, a process that begins with ordinary stars. Stars are not static. They are dynamic systems. For most of their lives, they exist in balance. Gravity pulls inward. Energy from nuclear fusion pushes outward. This balance can last for billions of years. Over time, a star uses its fuel. Fusion slows. Energy production decreases. Pressure weakens. Gravity continues, unchanged. As balance fades, the star begins to contract. Not suddenly, not violently, just slowly, as gravity takes over. This contraction marks a transition. Not all stars become black holes. Small stars cool quietly. Medium stars leave behind dense remnants. Only the most massive stars continue collapsing beyond all resistance. The fate of a star depends mainly on its mass. More mass means stronger gravity. If gravity becomes strong enough, no known pressure can stop collapse. When collapse reaches this point, space itself bends deeply. A boundary forms. Beyond this boundary, escape is no longer possible. A black hole is born. There is no dramatic instant, no explosion at the boundary itself. The event horizon forms quietly. From the inside, nothing special is felt at that moment. To a distant observer, the collapse appears to slow. Time stretches. The formation of the black hole seems to take forever. This is a result of how time behaves near strong gravity. A black hole is not destroyed matter. Matter still exists, but it exists in a new state. Space and time around it behave differently. Some black holes did not form from stars at all. They formed much earlier, when the universe itself was young. These black holes formed from direct collapse of dense regions. Some theories suggest small black holes may have formed shortly after the universe began. These would be ancient, quiet, hard to detect. Their existence remains uncertain, but possible. At the centers of galaxies, including our own, lie supermassive black holes. These did not form from a single star. They grew over time, through mergers, through slow accumulation of matter. Black holes can grow. They can merge with others. They can absorb surrounding matter. This growth is usually slow. Accretion happens gently. Black holes do not pull things in more strongly than other objects with the same mass from a distance. Their gravity is ordinary, only very close. Does their extreme nature appear? Black holes are not anomalies. They are natural outcomes of gravity working patiently. They are part of the universe's normal behavior. We associate collapse with destruction, but cosmic collapse is a reorganization, not an ending. just a change in form. Imagine a star quietly reaching the end of its life and gently transitioning into a black hole. No violence, just inevitability. Every black hole is defined by a boundary, not a wall, not a surface, not something solid, just a quiet boundary in space, called the event horizon. The event horizon marks a simple idea. It is the distance from the black hole, where escape becomes impossible, not because of force, but because space itself is curved too deeply. One of the most surprising facts about the event horizon is how ordinary it feels. Locally, if you were falling freely, you would not notice. The moment you crossed it, there is no sound, no flash, no signal. The event horizon emits no light. It reflects nothing. It is not made of material. It is simply a location, defined by gravity. This makes it impossible to see directly. Outside the event horizon, light can escape. Inside, all paths lead inward. Even light follows these paths. This is why black holes appear dark. The event horizon does not block. It does not repel. It does not resist. It simply marks a point where future paths can no longer lead outward. Imagine floating down a gentle river. Far upstream, you can still paddle back, but as the current strengthens, a point arrives where paddling is no longer enough. That point is like an event horizon. Nothing dramatic happens there, but return becomes impossible. To a distant observer, something strange appears. As an object approaches the horizon, its motion seems to slow. Its light stretches and fades. Time appears to stretch. This is not illusion. It is gravity affecting time. From the falling object's perspective, nothing unusual happens at the horizon. Time feels normal. Motion feels smooth. The crossing happens quietly. Both perspectives are correct. Gravity affects time differently, depending on location. This difference is one of the deepest mysteries of black holes, because nothing escapes. Once it crosses the horizon, information appears trapped. This leads to deep questions. Does information truly disappear? Or is it preserved in some way? These questions remain open. The event horizon is not the center. It is far from the core. Inside the horizon, space continues inward. The journey is not over. The size of the event horizon depends on the black hole's mass. More mass means a larger horizon. Supermassive black holes have horizons so large that crossing them could feel gentle. Event horizons are not dangerous by themselves. Tidal forces depend on size. For very large black holes, these forces can be weak at the horizon. The horizon does not destroy. It simply defines a region from which return is impossible, a boundary of futures. Understanding the event horizon helps us understand limits, limits of observation, limits of escape, limits of knowledge. Black holes teach us that space and time are flexible. They are shaped by mass. They respond gently. but profoundly. Imagine a calm boundary in space, not visible, not dramatic, just quietly marking a point of no return. When we think of falling, we imagine moving downward, toward the ground, pulled by gravity. This idea comes from everyday experience, but near a black hole, falling is something else. Gravity is not a pull downward. It is the shape of space and time. Objects follow the curves. They move along paths that feel natural, even effortless. This is true everywhere. When something falls toward a black hole, it is not being dragged. It is following the geometry of space. The path leads inward, because space itself curves inward. In free fall, there is no sensation of force. Astronauts in orbit feel weightless, because they are falling continuously. The same is true near a black hole. Falling feels calm, as an object falls toward the horizon. Nothing dramatic is felt. Motion remains smooth. Time continues normally. For the falling observer, the experience is uneventful. To a distant observer, the object accelerates. To the falling observer, nothing feels different. This difference comes from how gravity affects time and space. As the object falls, space guides its motion. Paths tilt inward. The direction of forward gradually points toward the center. Near a black hole, falling is not moving downward. It is moving forward in time, along curved space. After crossing the horizon, the center lies in the future. Inside the horizon, all future paths lead inward, not because of force, but because of geometry. Turning around is not possible, just as one cannot turn toward the past. This inevitability is not frightening. It is simply how space-time works. In this region, everything follows the same rule. Black holes do not suck. They do not pull violently. They do not drag objects in. Objects must already be close, and already moving inward. To fall in, outside the horizon, stable orbits can exist. Objects can circle a black hole, just as they orbit stars. From afar, a black hole behaves like any other mass. Closer in, paths curve more sharply. Orbits become unstable. Eventually, motion inward becomes unavoidable. Still, no sudden force is felt. Everything about falling into a black hole is gradual. There is no sudden drop, no jolt, no warning, just smooth motion. To distant observers, the fall seems slow. Light stretches. Motion appears to freeze. To the falling observer, time continues normally. Both views are correct. Understanding falling helps remove fear. Black holes are not violent traps. They are regions where geometry dominates. Imagine floating gently, following a smooth path, with no sensation of force, no urgency. In everyday life, time feels steady. Seconds follow seconds. Minutes pass quietly. We rarely notice time itself. It simply flows. In the universe, time does not flow at the same rate everywhere. It depends on gravity. Stronger gravity slows time. We usually do not notice this, because Earth's gravity is gentle. Gravity does more than shape space. It shapes time. Where gravity is strong, time moves more slowly. This is not theory. It has been measured many times with great precision. Near a black hole, gravity becomes extremely strong. Space curves deeply. Time slows dramatically. The closer one gets, the slower time flows, relative to distant observers. Imagine two clocks, one far away from the black hole, one falling toward it. The distant clock ticks normally. The falling clock ticks more slowly. From the distant observer's point of view, to the falling observer, time feels normal. Heartbeats feel the same. Thoughts flow normally. There is no sensation of time slowing. From far away, the falling object appears to slow. Moments stretch. Motion becomes gradual. Light becomes dimmer, redder, softer, as the horizon is approached. This stretching becomes extreme. To the distant observer, time appears to almost stop. The image fades. Slowly, quietly. From the falling observer's perspective, the horizon is crossed. In finite time, no pause, no delay. Time continues normally. Both experiences are real. Both are correct. This is one of the deepest ideas in modern physics. Reality depends on perspective. Near a black hole, time and space exchange roles. Direction toward the center becomes as unavoidable as the flow of time. The future points inward. Our intuition evolved. In weak gravity, we expect time to be universal. Black holes challenge this assumption. They reveal that time is flexible. Although descriptions differ, no contradiction exists. For lived experience, no observer sees anything impossible. Physics remains consistent. Time does not shatter. It does not stop. It does not reverse. It simply flows at different rates, in different regions. Black holes amplify effects that exist everywhere. They make subtle truths visible. Time dilation exists near Earth, but black holes reveal it clearly. Understanding time near black holes helps us understand time everywhere. It shows that time is not absolute. It adapts to the shape of space. Time is not fragile. It does not need protection. It flows naturally, according to structure. This realization can feel grounding. Imagine time flowing like a river, slower in deep valleys, faster on open plains, always moving forward. The word spaghettification often sounds alarming. It appears in headlines. It sparks imagination. But the reality behind the word is calm, mathematical, and gentle in nature. Spaghettification describes a difference in gravity. Gravity is slightly stronger, closer to a massive object, than it is farther away. This difference is called a tidal effect. It exists everywhere, even on Earth. The moon causes tides. On Earth's oceans, one side of Earth feels slightly stronger gravity than the other. That difference stretches water, This is a tidal effect. Near a black hole, tidal effects become stronger. Gravity changes more rapidly over short distances. This difference can stretch objects along one direction and compress them along another. Spaghettification is not a moment. It is not an instant. It happens gradually as tidal forces increase. There is no sharp boundary where stretching suddenly begins. An important detail is often overlooked. Tidal forces depend on size. Small black holes have very strong tidal effects near their horizons. Large black holes have much gentler tidal effects at the same boundary. Near a supermassive black hole, the event horizon can be crossed without strong tidal forces. Spaghettification would occur much deeper inside. This surprises many people. Nothing tears suddenly. Nothing explodes. Matter responds to gravity smoothly, according to physical laws. The process is gradual and predictable. Spaghettification sounds extreme because we imagine human scale. At cosmic scale, it is simply geometry. Space curves differently over different distances. Tidal forces stretch objects along the direction of gravity. They squeeze objects perpendicular to it. This happens quietly over time. The name exists because it is memorable. It helps visualize elongation along one direction, but the name exaggerates the emotional impact. There is no intention, no targeting, no consumption. Objects follow paths shaped by space. That is all. Even now, Earth experiences tidal forces from the moon and sun. They are just very small. Black holes reveal what gravity can do when concentrated. Physics does not dramatize. It describes relationships. Spaghettification is simply a description of gradients in gravity. Understanding tidal forces helps remove fear. Black holes do not destroy in unpredictable ways. They follow rules precisely, quietly. Spaghettification does not begin at the event horizon by default. Its location depends on mass. This reinforces the idea that the horizon itself is not dangerous. Let go of imagery. Think instead of smooth curves, gradual change, gentle stretching of space. Crossing the event horizon does not feel like crossing a boundary. There is no sound, no sudden change, no signal. From the inside, the universe continues quietly. Inside the event horizon, something subtle happens. Directions change meaning. The direction toward the center becomes unavoidable, like the passage of time. Just as time moves forward, motion inward continues. Outside the horizon, you can choose direction. Inside, all future paths point inward. This is not because of force. It is because of geometry. Inside a black hole, the center is not a place you can avoid. It lies in the future. Moving forward in time means moving inward. This is difficult to imagine, but perfectly consistent. Physics does not suddenly break. Local conditions remain smooth. Matter behaves normally. For a time, the environment feels quiet, ordered, predictable. For an observer inside, time flows normally. Clocks tick. Thoughts follow one another. Nothing feels frozen or stopped. Inside the horizon, the journey toward the center takes a finite amount of time. This duration depends on mass. Larger black holes allow longer journeys, while inside, signals cannot travel outward. Light, radio, any information, all paths lead deeper in. This isolation defines the horizon. Despite popular images, the interior is not chaotic. There are no swirling tunnels, no violent storms, just curved space, guiding motion gently, in free fall. Gravity is not felt. Objects feel weightless. This remains true inside, until tidal effects become significant. The interior experience depends on black hole size. Supermassive black holes are gentle near the horizon. Smaller black holes have stronger tidal gradients sooner. Nothing universal happens at a fixed point. Everything depends on scale. Mass shapes the experience. This reinforces the calm logic of physics. At the very center, current physics becomes uncertain. Equations predict a singularity, a point where density becomes extreme. But this prediction may not be final. Science is honest. It tells us where understanding ends. Inside the deepest core, new physics may apply. This uncertainty is acknowledged, not feared. Unknown does not mean dangerous. It means unexplored. The universe has many regions we have not yet described fully. This is normal. A black hole is not separate. It is not outside reality. It is part of the same universe, obeying the same fundamental laws. Understanding the interior removes mysticism. Black holes are not portals, or gateways, or endings. They are extreme, but natural, states of space and time. Imagine moving calmly, forward in time, through curved space, without resistance, without fear. The word singularity often sounds final. It suggests something infinite, something broken, something overwhelming. But in physics, a singularity has a quieter meaning. A singularity does not mean something explodes, or disappears, or ends. It means our equations stop giving clear answers. It marks the edge of what current models can describe. A singularity is not a thing. It is not an object you could touch. It is a prediction within mathematical descriptions. It tells us where understanding needs to improve. According to present equations, matter becomes extremely dense. Near the center of a black hole, space curves intensely. Time behaves in unfamiliar ways. At some point, the math produces infinities. That point is called a singularity. In physics, infinities are warnings. They tell us a model is being pushed beyond its range. They do not necessarily describe physical reality. Similar infinities appeared before in other areas of physics. Each time, they were resolved by deeper understanding. Singularities may be similar. No signal from a singularity can reach outside. No measurement can be made directly. Everything we say about singularities comes from extrapolation, not observation. Inside a black hole, matter does not suddenly vanish. It continues along paths, shaped by spacetime. The singularity represents the end of those paths. In our current description, some theories suggest singularities may not exist as literal points. They may be replaced by extremely dense regions or new structures. These ideas remain speculative, but calm. One reason singularities appear is because two theories meet. General relativity describes gravity. Quantum physics describes the very small. They do not yet fully agree. Singularities sit at this boundary. This boundary is not a failure. It is a frontier. It shows where new understanding is needed. This has always driven progress. There is no need to imagine crushing or tearing or collapse beyond imagination. Those images come from fiction. Physics remains restrained, precise, careful. Inside the horizon, time continues until the limits of description are reached. At that point, the concept of time itself may need redefining. Singularities are hidden behind event horizons. They cannot influence the outside universe. They do not threaten stability. They do not leak effects outside black holes. Physics works beautifully. Stars form. Galaxies evolve. Time flows normally. Singularities do not disrupt this calm order. The universe is older, larger, and deeper than any single theory. That is not frightening. It is grounding. Imagine reaching the edge of a map where the page ends, not because reality ends, but because the map does. At the center of most galaxies, there is a black hole, not small, not ordinary, but supermassive, millions or billions of times more massive than the Sun. At the center of the Milky Way, there is a supermassive black hole. It remains quiet, invisible, yet its influence shapes the motion of stars nearby. Supermassive black holes were not seen directly at first. They were discovered by observing the motion of stars. Stars orbiting something unseen, moving very fast around an empty-looking region. Only something extremely massive, yet invisible, could explain these motions. A black hole fit the evidence perfectly, despite popular imagery. Supermassive black holes do not consume entire galaxies. They are small compared to their galaxies. Their gravitational reach is limited. Most stars remain unaffected. Most supermassive black holes are quiet. They do not actively absorb matter. They sit calmly in gravitational balance. Sometimes, matter falls inward. Gas and dust spiral in slowly. As this material heats up, it emits light. These active phases can make black holes appear bright. Matter does not fall straight in. It forms a disk, slowly spiraling inward. Friction heats the disk. Light is released. This light allows us to detect black holes. Some supermassive black holes produce narrow jets of energy. These jets are not universal. They occur under specific conditions. They are not signs of violence, but of structure. The growth of supermassive black holes takes billions of years. They grow slowly. They merge with others. They evolve alongside their galaxies. There is a deep connection between galaxies and their central black holes. Their masses are correlated. This suggests they influence each other's growth. Despite this link, black holes do not dominate galaxies. They are part of a larger system. Gravity, gas dynamics, and star formation all play roles. These black holes help us understand a galaxy evolution, a large-scale structure, and the history of the universe. They are cosmic markers of time. Some supermassive black holes formed very early. They existed when the universe was young. Their presence helps constrain cosmic timelines. The existence of early supermassive black holes matches the age of the universe, derived from other methods. Once again, different lines of evidence agree. Despite their mass, supermassive black holes are calm. They do not disturb the everyday motion of galaxies. They are anchors, not destroyers. Imagine the center of a galaxy, vast, quiet, with stars orbiting gently around an unseen center. Black holes and galaxies are not separate stories. They evolve together over billions of years, quietly, gradually, from the early universe onward. As galaxies formed, black holes grew with them. Neither came first in isolation. They developed as parts of the same system. Gravity links everything. It shapes galaxies. It feeds black holes. The same gentle force organizes stars, gas, and dark matter. Most large galaxies contain a central black hole. Its mass correlates with the galaxy's properties. This relationship suggests long-term interaction. When black holes are active, they release energy. This energy can gently influence surrounding gas. It may slow star formation or regulate growth. This is called feedback. Feedback is not violent. It does not tear galaxies apart. It helps maintain balance. It prevents unchecked growth. These interactions happen over millions and billions of years. Nothing sudden, nothing dramatic, just slow adjustment. A galaxy is an ecosystem. Stars form, stars age, gas circulates. Black holes are part of this system, not rulers, not destroyers, just participants. Galaxies sometimes merge. When they do, their black holes may merge too. This process is slow. It unfolds over vast timescales. When black holes merge, they send gentle ripples through space-time. These ripples are called gravitational waves. They carry information, not danger. Gravitational waves allow us to listen to the universe. They confirm predictions. Quietly, precisely, they add another layer to our understanding, the existence of mature galaxies and their black holes tells us the universe has had time to evolve. Their complexity reflects age. Galaxies do not form overnight. Black holes do not grow instantly. Everything unfolds slowly. This slowness is essential. The universe is balanced. Even extreme objects fit into a larger harmony. Black holes do not break the system. They help shape it. Understanding this relationship removes fear. Black holes are not cosmic threats. They are components of a calm, ordered universe. Imagine a galaxy slowly rotating with a quiet center, holding everything gently in place. For a long time, black holes were thought to be completely silent. Nothing could escape them. Not light, not matter, not information. They were seen as perfect absorbers. But then, a quiet idea emerged. Hawking radiation does not come from inside a black hole. Nothing escapes the event horizon. Instead, this radiation arises just outside the boundary, in the fabric of space itself. Even what we call empty space is not truly empty. On very small scales, space is active. Tiny fluctuations appear and disappear. This is a normal feature of the universe. These fluctuations can briefly form pairs of particles. They appear together and usually disappear together. This happens everywhere, all the time, quietly, near the event horizon. Something subtle can happen. One particle of a pair may fall inward. The other may drift outward to a distant observer. This outward particle looks like radiation. For this to happen, energy must be conserved. The energy of the escaping particle comes from the black hole itself. This means the black hole loses an incredibly tiny amount of mass. This process is extremely slow. For large black holes, the effect is almost impossible to detect. The radiation is faint, gentle, barely present. Hawking radiation does not burn. It does not glow brightly. It does not warm surroundings. Its temperature is far colder than the cosmic background. Hawking radiation does not make black holes explosive. It does not destabilize galaxies. It does not change everyday physics. Its effect is subtle, over unimaginable timescales. This idea changed how scientists think. Black holes are not perfectly eternal. They can slowly, very slowly, lose mass. This does not make them fragile. It makes them part of time. Hawking radiation arises from combining ideas: gravity, quantum physics, and space-time. It sits at the boundary of our best theories. So far, Hawking radiation has not been observed directly. It is far too weak. But the theory is consistent, careful, and widely accepted. Hawking radiation suggests black holes are not separate from the rest of physics. They obey deep laws. They participate in the universe's evolution. Because black holes can lose mass, they have lifetimes. These lifetimes are enormous, far longer than the current age of the universe. Even the most extreme objects are not permanent. Given enough time, everything changes. This is not alarming. It is gentle. No black hole will evaporate anytime soon. The timescales involved are beyond imagination. This idea exists far beyond everyday concern. Hawking radiation is beautiful because it is quiet. It shows how the universe balances itself, even in extremes. Imagine space itself, softly active, calmly fluctuating, even near the darkest regions. After learning about Hawking radiation, a natural question arises. If black holes can lose mass very slowly over time, do they eventually disappear? Evaporation sounds active, but in this context, it is almost unimaginably slow. It is not steam rising. It is not a visible process. It is a mathematical consequence of tiny energy changes over vast stretches of time. The temperature of a black hole depends on its mass. Larger black holes are colder, much colder. Smaller black holes would be warmer, but still incredibly cold by everyday standards. Supermassive black holes, like those at the centers of galaxies, are colder than almost anything else. They absorb more energy from surrounding space than they lose through Hawking radiation. For them, evaporation is effectively paused. If a black hole were isolated and no matter fell into it, it could slowly lose mass, but the time required is enormous, far longer than the current age of the universe, far longer than stars will shine. Right now, the universe is young. Black holes are growing, not shrinking. They gain mass from gas, dust, and mergers. Evaporation is irrelevant at this stage. Only in the far future, when stars have faded and galaxies are quiet, might evaporation become noticeable. Even then, it would proceed gently. No explosion, no sudden ending. Some theories suggest that the very final moments of evaporation could be energetic, but this lies so far in the future that it has no practical meaning now, and these ideas remain speculative. Physics favors continuity. Processes unfold gradually. Even endings are slow. Black holes follow this rule. If a black hole evaporates, what happens to the information about what fell in? This question leads to one of the deepest puzzles in physics. We will explore it gently. Next, evaporation does not mean loss without trace. Energy is conserved. Something changes form. The universe balances itself. Black holes are not infinite, but they are persistent. They exist on timescales that dwarf everything familiar. This endurance gives them their quiet presence. Even the most extreme objects obey time. Nothing is frozen forever. Everything participates in the flow of the universe. Thinking about such long timescales can be humbling. It places human life into a broader context, not to diminish it, but to soften it. Imagine time stretching outward, far beyond stars, far beyond galaxies, with change occurring, slowly, almost imperceptibly. As scientists studied black holes more deeply, a quiet question appeared. Not loud, not alarming, just a gentle uncertainty. What happens to information that falls into a black hole? In physics, information does not mean knowledge or memory. It refers to the detailed description of a system, the exact arrangement of particles, their properties, their relationships, according to known physical laws. Information is never destroyed. It may change form. It may spread out. It may become difficult to recover, but it is not erased. Black holes seem to challenge this idea. If nothing escapes the event horizon, how can information ever return? If a black hole evaporates, what happens to what fell in? The paradox is not violence. It is not danger. It is a disagreement between two well-tested ideas, gravity and quantum physics. Both work beautifully in their own domains. Together, they raise questions. It is important to pause here. No experiment has shown that information is destroyed. The paradox exists in theory, not observation. Many ideas have been proposed. Some suggest information is stored on the event horizon. Others suggest it is encoded in Hawking radiation, very subtly. Some suggest deeper principles we do not yet understand. There is no rush to resolve this. The paradox does not affect daily physics. It does not threaten stability. It does not imply catastrophe. It simply invites deeper understanding. Science grows slowly. Questions appear, are examined, and sometimes wait. 4 generations. The information paradox is one such question. This paradox is not a failure. It is a sign of progress. It shows how far understanding has reached and where it can still grow. Once again, black holes act as teachers. They guide attention to the boundaries of knowledge. They reveal where ideas meet. Regardless of the answer, the universe remains calm. Stars form, galaxies evolve, time flows. Nothing depends urgently on solving this question. It is possible to hold complexity without tension, to accept uncertainty without discomfort. The universe allows this. Not everything needs resolution. Some questions are meant to remain open. For now, this openness creates space, not anxiety. Most modern approaches suggest information is preserved in ways we do not yet fully see. This preserves consistency. It preserves calm at the edge of understanding. The best response is patience, curiosity without urgency. Imagine information not as data, but as gentle structure, quietly woven into space and time, never truly gone. When we think about black holes, it is natural to wonder what role they play in the distant future. not the near future, not anything close to human time, but the far future, where time stretches beyond imagination. The universe is not static. It evolves, slowly, patiently, over enormous spans of time. Stars are born, and stars fade. Galaxies drift apart. Black holes remain. Long from now, star formation will slow. Gas will become scarce. Galaxies will grow dimmer. The bright era of stars will gradually end. Black holes will outlast stars. They do not burn fuel. They do not shine. They simply remain, quietly, as gravity-bound structures. As time moves forward, the universe becomes calmer. Less light, less activity, more space, more silence. Black holes fit naturally into this quiet future. Over immense spans of time, black holes may merge. Galaxies will collide. Slowly, gently, their central black holes will spiral together. These events will be rare and far apart. When black holes merge, they send out gravitational waves, not sound, but ripples in space-time. These ripples fade, leaving no disturbance behind. The universe absorbs them calmly. As expansion continues, galaxies will drift beyond view. Each region of space will become more isolated. Black holes will remain, but far apart, each in its own quiet domain. Only in the farthest future, when the universe is cold and nearly empty, will Hawking radiation begin to matter. Even then, the process is slow. If evaporation occurs, it will take longer than any familiar timescale. Black holes will shrink quietly. No sound, no spectacle, just gradual change. There is no final explosion, no sudden disappearance. The universe prefers smooth endings, transitions, not finales. Eventually, very little will happen. Space will be vast. Energy will be thinly spread. Time will continue, even if nothing changes. In some visions of the future, black holes are among the last complex objects to remain, quiet markers of a long history. Even in this quiet future, nothing is wasted. Energy is conserved. Information remains woven into the fabric of space. The far future is not frightening. It is peaceful, still, unhurried. Black holes belong to this peaceful vision. Thinking about deep time can soften the mind. There is no urgency, no race. Everything unfolds at its own pace. Human life exists in a bright, active era. That is not insignificant. It is simply a moment, held within a much longer story. Black holes are not endings. They are chapters, quiet ones. Imagine the universe, long from now, dim, spacious, silent, with black holes resting in vast emptiness. There is nothing left to explain, nothing to understand, nothing to remember. The universe does not require conclusions. It continues quietly. Black holes remain, not as threats, not as mysteries, but as regions of calm gravity. They do not demand attention. They simply exist. Space continues to stretch. Distances grow. Galaxies drift apart. Slowly, without effort. Time passes. Without announcement. Seconds fade into minutes. Moments drift into rest. The universe holds stars, and planets, and space between them. It holds silence and motion. Together, there is no need to listen, no need to follow. Thoughts can soften and drift away. Nothing needs action. Nothing requires response. Everything continues at its own pace. Darkness is calm. Stillness remains. No interruption. You can rest now. Everything continues without effort.
you.